Howdy folks. Once again, here we are. We're going to learn a little bit of calculus, and this is one of my favorite subjects in all of calculus. It's called related rates, and I love it so much we're actually going to do it for 2 whole class sessions, which means today we're going to learn related rates part 1. So today I'm just going to get you sort of waist deep in calculus. You have already learned implicit differentiation, which is necessary to be able to do related rates. And I'm going to show you right now how we solve related rates problems, okay? So I have a 7-step procedure. Oh my goodness, Mr. Ryan, 7 steps? Yeah, but trust me on this. Most of the steps are sort of very, very easy steps. I like to go one baby step at a time. But here's what I want to tell you is that related rates, the idea in related rates is that you have 2 derivatives that are related to each other. And I'll point that out when we see the related derivatives in the things that we're doing. Okay, but the idea is that you have rates of change, and a rate of change is a derivative. A derivative is a rate of change, and a rate of change is a derivative. So for example, if we have a circle, we understand that a circle has a radius, right? Has a radius. A circle also has, so a circle has, oops, write it like this. A circle has a radius. A circle also has a circumference. And a circle has area. Now, radius is a distance, circumference is also a distance, but area is not a distance. Area is a second dimension variable, and it is a distance times a distance, like base times height. In this particular case, for a circle, it's radius times radius, because we have r squared, right? In fact, let's throw the formulas up here. Circumference is equal to 2 pi times radius. Area of a circle is equal to pi times radius squared. And what you can see here is this. See this equal sign here in this formula? This equal sign means that circumference is related to radius. Related. And the rate of change in radius is related to the rate of change in circumference. So they are related rates. Okay? Similarly, here with area, let's say the radius was changing. If the radius is getting larger, if the radius gets larger, the area will get larger. And that's just the nature of the relationship between area and radius with a circle. So, as the radius gets larger, it's changing. And because the radius is changing, it has a rate of change. The area is also changing. And because the area is changing, it has a rate of change. So because the radius is changing and the area is changing, the radius has a rate of change, and the area has a rate of change, and those 2 rates of change are related to each other. The reason they're related to each other is because area and radius are related to each other, and therefore their rates of change are also related. Hence, we have related rates. Now, this is a very important concept in engineering and also in economics, and I would probably guess that it's important in a lot of other areas of study as well. So, this subject of related rates is hugely important for anybody who's going into a math-related field. Okay, there's plenty of stuff out there on YouTube for you to be able to watch that can help you improve your knowledge of related rates. But I'm going to start you off real slow. We're going to start off with some really easy questions. And we're going to understand how to solve related rates. Okay, let's start off. I'm going to give you my 7 steps for solving related rates. All right, folks. Here is Mr. Ryan's 7-step procedure for solving any related rate problem. Well, really any related rate problem over time. So this is my 7-step procedure. Why don't you pause the video right now and write all these steps down in your notes. Okay? So now what we're going to do is we're going to do a couple problems, or I'm going to, excuse me, what we're going to do right now is I'm actually going to talk through these 7 steps and explain little bits of information. Then once you understand, or once you have a beginning understanding of the 7 steps, then we're going to do some simple problems and work our way up to some more difficult problems. Okay? So step 1 is identify all given rates of change. What I mean by that is if you're given a problem, it'll say something like this. The hypotenuse of a right triangle is increasing at the rate of 7 meters per second. That is a rate of change. Anytime you see the word per, anytime you see the word per, that usually indicates a rate of change. Miles per hour, meters per second, hot dogs per minute, miles per gallon. Any phrase that has variable per variable. So, variable like miles per variable like gallons, okay? Or units per units. That's probably a better way of saying it. Anytime you see units, units per units. All right, units. Millimeters per inch. Anytime you see units per units, you're looking at a rate of change. There are probably billions or trillions of these throughout the universe. Okay, so you have to broaden your mind. Now, mostly the ones we're going to be dealing with, these units over here are always going to be time units. So you're going to have miles per hour, feet per second, meters per minute, whatever. Okay, it's always going to be and typically it's going to be, well, it could be degrees Fahrenheit per minute. It can be any unit over here per a time variable. So whenever you have that, you see the word per, anytime you see the word per, that's going to indicate that you are dealing with a rate of change. So here's what you have to do. The related rates problems typically give you 1 or 2 rates of change to start with, and then they expect you to find a second or third rate of change as an answer. And that's where step 2 comes in. Identify the unknown rate of change. Now, here's what you have to understand, is that your rates of change look like derivatives. Now, you're accustomed to seeing, let me get a different color here. You're used to seeing dy dx, right? dy dx, that means a derivative, right? This is the change in y over the change in x. But our derivatives, see, this would be y per x. That's what that would be, y per x. But because we're doing something per time, because time is our independent variable, we're going to have a t down here. And then the letter that is in the numerator here with this d is whatever variable you're dealing with. Like, for example, radius. If it was the rate of change in radius, it would be dr dt. So dr dt is the rate of change in radius. Okay? Well, what would the rate of change in area be? What would the rate of change in area be? Well, that would be dA dt. d dt of A, the rate of change in A, in area. Okay? Well, what would the rate of change in circumference be? Circumference. Okay, that would be dc dt. It's always d something dt. If we wanted to know the rate of change in pillows, what if we wanted to know the rate of change in pillows? Well, that would be d pillows dt. That's the rate of change in pillows over time. What if we wanted to know the rate of change in ice cubes? Okay, ice cubes. We know that the number of ice cubes are changing over time, and the rate of change in ice cubes would be d ice cubes dt. There we go. It's always d dt with something right here. And if it's circumference, then it's dc dt. If it's volume, if it's the rate of change in volume of something, it's dv dt. That's the rate of change over time in volume. I hope you're getting the idea here, okay? And so what happens is this, is in every problem, you're typically given a rate of change in something. So what if you were told that the rate of change in the side length of a square is 7 meters per second? The rate of change in the side of a square. Well, that would be ds dt, and it would be 7. So what we would do is, for step 1, identify all given rates of change. We would write ds dt is equal to 7. And then let's say that the question is asking about the rate of change in the area of a square. Well, it's saying, what is the rate of change in the area of the square, right? Well, that would be the unknown rate of change. And we would write dA dt equals, we don't know. Question mark. We don't know. That's what we're trying to find out. In fact, that's what we're trying to solve for down here in step 7. Solve for the unknown rate of change. In step 7, you are solving for the rate of change that you identified in step 2. Okay, so first we need to identify get any rates of change that are given. Sometimes you're given more than one. You got to write those down with their numbers. By the way, if the question said that the side length of a square is decreasing at 7 meters per second, then we would put -7, because when something has a rate of change where it's decreasing, if something is changing to where it's getting smaller, then its rate of change is negative. And so we would put -7. So we got to identify any given rates of change, their values. Then we have to identify the rate of change that the question is asking you to identify or to answer for. Okay? All right, got that? All right, what about step 3 here? Step 3 says identify a formula that relates the variables in these rates. So if this one is ds dt and this one is dA dt, what we're looking for is a formula, some mathematical formula in the universe of math that relates this variable to this variable. Are S and A, are they related to each other? And the answer is yes, they are related to each other. The side of a square and the area of a square are related to each other. There's a formula. It's the area of a square. The area of a square is equal to side squared. So what you have to do is, sometimes on these problems, you have to go into a textbook or go out there into the world and find some formula that relates this variable to this variable. And then that is the formula that you're going to use for that problem. Step 4, plug in values for any unchanging variables. Sometimes some of these formulas have like 3 variables or 4 variables or 5 variables. And sometimes some of those variables are not changing. For example, if you had a triangle, the area of a triangle is 1/2, excuse me, I was about to write base times height. It's not what it is. 1/2 base times height, right? Well, what if the height of the triangle was not changing? What if the only thing changing was the base of the triangle? Well, then the area is changing and the base is changing, but the height is not changing. So for step 4, if you were told that the height of the triangle was 12, then what you would do is you would rewrite the formula as area equals 1/2 base times 12. And then, of course, 1/2 of 12 is 6. So you would now have area is equal to 6 times base. Okay? So you won't always do step 4. For example, with the area of a square, we can't plug anything in for A or S. If one of these variables is not changing, then the other one is not changing either. Okay? So we always have to consider the possibility that one of the variables in the formula from step 3 is not changing. So we want to plug that, the given value for the unchanging variable, plug that in. Then, step 5, find the derivative of the formula. All right, well, let's say that we were still dealing with a equals s squared. Well, to find the derivative of the formula, you have to apply a derivative rule. But you're finding the derivative with respect to t, not with respect to a and not with respect to s. Remember when we did implicit differentiation and we had something like y to the third power plus 7x squared is equal to 2x minus 9y squared? When we were trying to find d dx, we were doing the derivative with respect to x. So dy dx, okay? Whatever this letter down here is, that's the with respect to number. So this is with respect to t, this is with respect to x. So whenever we did the derivative of a term that had that letter in it, we just did the derivative rule, nothing special. The derivative of 7x squared is 14x, so we'd have plus 14x equals the derivative of 2x is 2. But if you recall, when we did the derivative of a letter that was not the letter in the denominator, we're looking for dy dx. Whenever we would do the derivative of a term that had a letter that was not in the denominator, we would find the derivative as normal. The derivative of y to the third is 3y squared, and then we would have to put a conversion factor on for the rate of change. And the conversion factor would be dy dx. It would be d this letter over d this letter. And so that's one of the things we have to do here, because we are going to d dt each term. d dt. Not d dx, and not d dA, and not d ds. We're doing d dt. Therefore, every single one of these is going to have a d, this letter, with a dt on the bottom. So the derivative of a is dA dt. And the derivative of s squared is 2s. That's the derivative, right? If this was x squared, wouldn't the derivative of that... Wouldn't the derivative be x, or excuse me, wouldn't it be 2x? Yes. And therefore, the derivative of s squared is 2s. But because we're doing the derivative with respect to t, we have to put a ds dt on the term. And this is now the derivative of this with respect to t. Okay? Now, in fact, let's do a couple more so that you can get a feel for it. Let's say that we had the circumference formula. Let's say we had c equals 2 pi r. Okay, well, the derivative of c is dc dt. The derivative of 2 pi r is 2 pi. Remember, 2 pi r, this is r to the first power. What's the derivative of 3x to the first power? Isn't the derivative of 3x to the first power just 3? Didn't you learn that? That's the power rule, right? That the derivative of a coefficient times a variable to the first power is just whatever the coefficient is. That's the slope. That's the rate of change. So, in this case, the coefficient of r is 2 pi. And therefore, the derivative of 2 pi r is just 2 pi. And then we have to slap on a dr dt. Just like we had to slap on a dy dx when we were doing implicit differentiation and we were doing the derivative of a y term. So the derivative of the circumference is dc dt is equal to 2 pi dr dt. All right, what about the derivative of the volume of a sphere? How about volume is equal to 4/3 pi r cubed? Well, the derivative of v is just dv dt. And this thing right here, that's just one term, so we got to do the derivative of that. We got to do 3 times 4/3. Well, 3 times 4/3, doesn't that just cancel the 3 here and give us 4? It's just 4. So the derivative of 4/3 pi r cubed, really tired of that thing falling down, but of course it's my fault. It's not the towel's fault. 3 times 4/3 is 4 pi, and then we have to reduce the power by 1. R to the third becomes r to the second. So that's r squared, and then dr dt. We have to slap on a dr dt because this is not the letter t, it's the letter r. Therefore, we have to put on a conversion factor for our rate of change. Okay? So these are examples of how to find the derivative of your formula. Step 6, plug in all given and implied values. So now that you have a formula, now that you have dv dt equals 4 pi r squared dr dt, here's what I want to show you. Here we have 3 variables. We have this, the rate of change is a variable. dv dt is a single variable. It's one thing. It is the rate of change in volume. dr dt is a single variable. It's the rate of change in radius. And r is also a variable. Now pi, that's a constant. 4, that's a constant. Okay? The square on the r, that's just the square. That's the exponent. So really we have 1, 2, 3 variables. And typically we have to plug in for all but one of those variables. All but one. So we would, in order to find the rate of change in volume, we would have to plug in for the radius and plug in for the rate of change in radius. Typically, the rate of change that you're plugging in for comes from step 1, one of the given rates of change. That usually gets plugged into your step 6 of the problem. And then in step 7, all you do is solve for the one thing that you didn't plug in for. And then you have your answer. So here's what we're going to do right now. We're going to do about 12 different examples. I know that that's a lot of examples, but it's going to be good for you and you're going to learn a lot, okay?